Hello, welcome back. Today we're going to look at the zeros of polynomial functions. So if you remember, the zeros can also be called the solutions, the roots, or the zeros. Oftentimes we'll see them on the graph. So if we have the function here, f of x equals x times x minus 4 times x plus 3, this is in factored form. So we can set this equation equal to 0. And if we know that this equals 0, well, then we can set each factor equal to 0. So I'm setting every parenthesis and the x equal to 0. So I know that x equals 0, that's going to be 1 x-intercept. X can equal 4, and then x can equal -3. If you remember, this has a degree of 3. It's going to be an x cubed, or a cubic function. And we know that these values are going to be the x-intercepts. If we were going to FOIL this out, well, we know that we'd have x times x times x. So the degree would be 3, and that power would be x cubed. So it's going to be positive. So if we know it's positive and odd, we know that this function is going to have a left arm down. So as x approaches -infinity, y will also approach -infinity. And we know that the right side is going to go up. So as x approaches infinity, f of x approaches infinity. And the x-intercept is where this function is going to cross the x-axis. So that would be a good sketch of the graph. Now there's something tricky with the multiplicity. And that means that we can have a 0 that is a double root, a triple root, a quadruple root, and this affects the graph in a huge way. If the root, or the 0, is odd, the function is going to cross the x-axis. It's going to go through that root. Versus if the root is even over here, the graph is going to make a turning point on the x-axis. So it's essentially going to touch the x-axis. So I showed a couple examples. So if we know that x plus 1 raised to the 5th power, 5 is an odd number. That's what we're looking for, that exponent. Well, we know that this number, this 0, is -1, so it's going to go through. Versus over here, if this b was 3, the exponent is even. So it's going to touch when x equals 3. All right, one more example, and just looking at functions. So here we have the graph and the equation. And you can tell that this function is a cubic, just like we graphed before. So it potentially has 3 real roots, but we only see 1 x-intercept here at 2. So there has to be 2 other roots, but they're not going to be real. They're going to be complex. So to find those 2 other roots, we're going to take this original function and we're going to divide this by the real root. And if you remember, in the last section, when we divided, we used synthetic division. So I'm going to put this 0 here in the box. This is 2. I'm going to put that number in the box. And if you remember, when we set up our synthetic division, we look at the coefficients. So this is 1, 1, -3, -6. Now remember, for synthetic division, we're going to bring down the 1. We're going to multiply and keep adding going down. And you could tell that this is going to have a remainder of 0, meaning that this is a factor. So we know that this function can be rewritten as x minus 2, because that was the 0 that we could see in the graph. And then what's left over is x squared plus 3x plus 3. Well, we can't factor that. So if we can't factor it, we're going to use the quadratic formula. And if you remember the quadratic formula, we have to identify the a, b, and c, and we can plug into the quadratic formula. So x equals negative 3 plus or minus 9 minus 4 times 1 times 3 all over 2. Now when we simplify this, we get negative 3 inside the square root. So if you remember, those are going to be imaginary roots. We also say complex roots. So I'm going to rewrite it as negative 3 plus or minus I root 3 over 2. And remember, that's just two of the roots, two imaginary roots. We found one of the real roots over here on the graph, and we proved it with synthetic division. So if we're going to give all three roots, 2 are complex, 1 is real, we can write it as negative 3 plus or minus I root 3 over 2, comma 2. So just as a reminder, when we look at the zeros of polynomials, we can have real zeros or we can have complex zeros. And I also write down imaginary to differentiate those two. The key thing that we learned today was the multiplicity and seeing how that affects the graph. So remember, if the degree of this exponent is even, it's going to have a turning point. It's going to touch the x-axis. Versus if the degree is odd, or this exponent's odd. This is going through at B, this is going through at C. So crossing the x-axis. Well, I hope this lesson was helpful, and I'll see you all in class.